All right, so I started the process. All right, so yeah, free body diagrams. As I said the other day in class, and I truly believe this, the free body diagram setup is 50% or more of your solution. It's that important before you even apply any math, because you're analyzing what's going on, and then it's just kind of stepping you through it. So then we talked about equilibrium of collinear forces. You're probably not going to see anything like that so much in problems too much. We're dealing more with the other kind. So the concurrent, we spent a lot of time with that the other day, and also the parallel force systems. So hopefully you've had a chance to take a look at that. And as I said, we can answer some questions today, and I can also answer some questions on Thursday, okay? So what we have not hit at this point is the non-concurrent. So we're going to take a look at non-concurrent. Actually, the solution of those is not all that much different than a parallel force system. So you pretty much already understand the aspects of it. So let's dive into this. So again, we talked about, just understand that we talked about the concept of reactions. And when we're in the statics, we're looking at that concept of equilibrium. So what we're saying is that all the forces on a body have to equal zero, and that's in terms of either translation or rotation. And if you don't have that, you don't have statics. So the whole premise is based on the fact that nothing is moving, nothing is rotating. So that brings us to the concept, the general equations of equilibrium for two-dimensional equilibrium, which is what we're dealing with almost exclusively, is that sum of forces in the x have to equal zero, sum of forces in the y equals zero, and the sum of moments about any point. And actually that's, as we said, for two-dimensional equilibrium, that's actually the moment about the z-axis, okay? So the sum of forces in x and y are dealing with translation, sum of moments are dealing with rotation, and we're using that for solutions. So we don't need to talk about the three-dimensional equilibrium, although it does get more involved. So let's see. So we said the first step, problem solving, you identify the problem, what forces are desired, what you have, what reactions. Then you draw the free body diagram. And again, that's, so key. It's important. And then you apply equations of equilibrium, and you don't always use all three of these, okay? So it depends on the case. So for concurrence, remember, we only use sum of forces in x and sum of forces in y. When we get into parallel force systems, we're using x, y, and also moment. And when we get into the kind we're going to get into today, the non-concurrence, it will use the same process. And it will further potentially use the concept of transmissibility. Okay, so we'll see how that kind of comes into play. So drawing free body diagrams, I think we covered that pretty well. So you can basically isolate your body, and that's where it gets the term, and then you put the proper supports in. So supports are all critical as well. So this was an example. This is called a space diagram. Shows you your potential support here, and you've got to recognize what that is and what that is. And then you come over here and draw your free body and your free body representation, because pin is at A, this guy has 2 reaction points. And since this is a roller, you got 1. And the key idea with the roller, remember that if this thing is free to roll over this surface, the reaction always has to be normal to the surface, so 90 degrees, so it's either going to be up or down. It could be either way, but it's impossible for it to be left or right. And that could be a potential place that you're going to make a mistake. So the types that we talked about, the pin, the roller, the fixed, and the cable. Remember, a pin is also considered the same as a rough surface, if it tells you that in the statement of the problem, and a roller is considered smooth. But remember, it has to be normal to that contact surface. Fixed would be another name where you're talking maybe a cantilever. And the fixed support is kind of unique because it's going to bring in a moment as well. And then, of course, the cable, which we've done a lot with, it can only be in a tension direction. So this little diagram out of your book kind of shows you that. Just memorize it. Space diagram representation, the free body, roller, with its free body. Here's your fixed with its free bodies. And then there's your cable, okay? So we'll take a look at, now there's a couple problems that I think there's one or two out of the chapter. I don't know if we did this yet, but we might want to look at that today if you guys have a question on that one. Okay, also remember, sign convention is really, really important as we get into this. Forces can be considered any direction you want, but most people consider a force to the right positive and a force to the left negative. Kind of works with the same convention that we use for the rectangular coordinate system. And upwards is positive and downwards is negative. But it truly, you can do this any way you want as long as you're consistent throughout the problem. Okay, so I don't really care. But this is the way we're going to do it from a convention standpoint. And moments work the same way. A lot of people use counterclockwise or clockwise positive, counterclockwise negative, but you can swap that off. So it really doesn't matter as long as you're consistent. As long as you're consistent. Okay, so we talked about the collinear force system. We're going to talk about this two-force member thing. That's coming up in chapter 4 as we get into trusses and truss analysis. So we're going to be talking about this concept of compression and tension. For now, it's not as important for us, but just remember that this would be what we call a collinear force system, where your forces are acting along the same line of action. And force static equilibrium, if this is force F, this has to be force F also in an opposite direction. Okay. If they're pulling away from your member, your body, that's what we would call a tension member. If they're pushing in along that body's line of action, then that's what we call a compression member. And when we get into strength of materials, that will be important because you guys, I'm sure, all understand that certain materials respond or act differently to compression versus tension. Concrete being one of those examples. Very strong in compression, very weak in tension. So it's important to understand how these work and which direction they're going. Okay. All right, so concurrent force systems, we spend a bit of time with that. The cable problems were concurrent force systems. They can be typically solved algebraic equations, which may be a little messier, but I think they're fairly foolproof. Then you have the trigonometric techniques. As long as you get your vectors stacked correctly, this works pretty effectively. But if you blow that, then that's going to be a problem. So I would say if you have a choice here, probably want to do it the algebraic way, even though it's a little longer. Usually it's a little bit more foolproof if you don't blow the math. Of course, any of them can be a problem, but I like using this method because it's pretty straightforward. So in this case, with the concurrence, you only have two conditions. You can use the sum of forces in X and sum of forces in Y. Okay, and the key thing too, anytime you have vectors that are not along an X or Y axis, the first thing you want to do is break them down into components. And that's going to be true with any of these things we talk about. Non-concurrent, concurrent, or parallel. You always want to get rid of those forces, or not get rid of them, but break them down. Okay. Okay, so I'm just we've already talked about this. So, all right, so the parallel force system is a specialized type of force system. We use a lot on beams and floors and roof design. But you always are going to use the three equations of equilibrium. Sum of forces in X, sum of forces in Y, sum of moments. And moments are usually going to give you what I call the distribution of what's happening between your reactions. So you do have to be aware of these types of things that can happen in your loading scheme. So typically we talk about either a concentrated load, also referred to as a point load, and then we have what's called a uniformly distributed load. Then you have what's called the uniformly varying load. So this one's easy to handle, the concentrated load, because it is what it is. But with a uniformly distributed load or the uniformly varying load, we need to get rid of that. We need to remodel it. So what we do is basically take these guys and bring them down into a concentrated load when we handle them as a parallel force system problem. Now, you will see when we get, I think, to chapter 11, when we start talking about shear moment diagrams, we will take these guys and break them down to do the reaction. But once we actually get into the shear moment diagram, we have to consider the uniformity here. So we'll bring that back later. Okay, but that doesn't apply to us right now. So these diagrams should be helpful. For concentrated load, typically you just know the force and you know its distance off of a side. And the free body representation, what you see on the space diagram is what you see on the free body. For the uniformly distributed load, we can't handle this. So what we do is we get rid of this and we model it with a reaction. So the uniform loads are very simple. Basically, you just take the distance over which it's acting times the load rate. So you can think of it as a rectangle. This is like your length times your height kind of thing. So you just multiply your distance over which it's acting times the load rate. That'll get you, notice this is in pounds per foot. This would be feet. So the units cancel out and you're left with pounds. Then this has to be applied in the right location, which is essentially the centroid or the middle of this. So this is acting over 5 feet, half of 5 feet, 2.5 and 2.5. Okay, so this is a simple case. The uniformly varying load is a little different. Sometimes that's called a triangular loading. Things like wind loads or snow that drifts would kind of produce this kind of thing. This again is something we have to handle, but the load rate, kind of can think of it, this is the load rate point right there. So you've got a distance over which it's acting times a load rate. What we're doing is calculating the area of this. So it's 1/2 the base times the height. So what we have is 1/2 the base times the height, where the load rate is your height, if you will. And then we have to act it properly. And where you act it is going to be dependent on the distance here. And the way it works with a triangle is 2/3 of the small end, 1/3 from the big end. So you would take 2/3 of 5 to get it from here to here, or 1/3 of 5 to get it from here to here. We're going to see why that is when we get into chapter 6, because we're going to talk about a process called centroids, or a concept of centroids, and we're going to see where that 2/3, 1/3 kind of comes from. Okay. None of your books have this kind of thing going on, so don't expect something like this on our test on Thursday. Okay. If you see anything, it's going to be point loads or it's going to be uniformly distributed loads. Okay. So just get a handle on this one primarily. I don't even think there's any book problems like this. So, all right. Any questions so far? This is just all review.
Good.
Okay, great. Stop me if you have a question, okay? And particularly if you ever want to go over a problem, because we'll do some more, okay? All right, so now we get to concurrent, non-concurrent. So this is new today, and as I said, it's really not all that different from the parallel force system. The only difference is that you may have to use something at the end. So this is a case where all of your forces don't intersect at any given point of concurrency, which is very similar. That's the same thing as a parallel force system, but the other thing that's going on here is they're not all parallel either. So when you have this type of system, just like normal, you're going to draw a free body diagram. That's going to be your first thing. You're going to then write algebraic equations, and the algebraic equations that you're going to use are going to be sum of forces in X, sum of forces in Y, and sum of moments, okay? Now, you may require the use of principle of moments, and that's just adding moments from one force plus another force moment. So we've been using principle of moments all along here. The thing we haven't been using too much is transmissibility. You don't use transmissibility when you are in the parallel force systems. So can anybody tell me what transmissibility means? We've talked about it. You've read about it. Can anybody give me the definition of transmissibility? No one has an idea? Okay. transmissibility is the concept that we can act a force anywhere along his line of action and have the same effect on that body, okay? So we can move that force anywhere along the line of action to get the same effect. Now, we have used that in chapter 2 to solve reactions, or not reactions, but resultants for non-concurrent problems. So we have used transmissibility where we took and slid the two vectors along the line of action. This is the concept of transmissibility, and it is not essential necessarily in the non-concurrence, but there are times that you will need to use it, okay? So I'm going to go through, let's see, a couple of problems, okay? And then we can look at some problems out of the book, okay? So let me, I think I'm gonna just kill this. I think we're done with this. And let me go over here. So I want to do a couple of examples, and then if you want to look at some out of the book, we can, okay? So let's assume that we have a ladder that is laying against a wall and it's loaded, and what we want to do is solve this, okay? So give me a sec here to draw some things up. I'm gonna put this in. So this is going to represent my ladder. So I'm going to do this really, really schematically. Okay, so we're going to say that ladder is laying against a wall like this, okay? Now we're also going to say a couple things about this. So it's sitting on a floor. So this is the floor that it's sitting on. And it's also leaning against a wall. Okay, so this is the wall that it's leaning against, and this is the floor that it's on. Now we're also going to load this with some loads. So we're going to have one load acting down here, and one load acting over here. Okay, so give me a sec here. I'm going to draw some stuff in here. So this guy's acting down, and this guy's acting down. We're going to say that this is 180 pounds here, and this is 150 pounds here. We also need to know some distances. So let me put a distance here. So that's where that guy's line of action is. This is the distance to the wall. This will be the line of action of that guy, and then this will be the distance at the foot of that ladder. Okay, so let me roll this up here, get this going. Okay, so we know some distances here. So we know that this is 4 feet, 2 feet, 2 feet. We're also going to assume that this has a height value on it. So from the floor to where the top of that ladder is, it's going to be 10 feet. Hardest part of some of these problems is drawing it. $10 feet. Okay, so there's my ladder. I've got it loaded. Now, we have to know a couple other things. One would be the reactions. So we're going to say that this floor is rough, because if it's smooth, it's going to be able to skate this way, okay? So this floor is rough, and up here, This is smooth. So what that means is this guy's going to be free to travel. Okay. So who can tell me how we're going to set this up? If it's smooth, the floor is smooth, the other area is rough. What's going on there? That's telling us about our reactions. Okay, so if this is rough, that's saying that this is a pin. Okay, and if this is smooth, this is saying this is a roller. So I'm going to get rid of this. And I'm going to get rid of that so I don't get that in my way. So who can tell me how we're going to model that then? This is a pin, so how many reactions does it have to have?
2.
2, okay. So in this case, I mean, it does kind of make sense that one would be like here, right? And we're going to have another one here. Does everybody agree with that? And I'm going to call these reactions. So I'm going to indicate this going up, and I'm going to indicate this going this way, which is arbitrary. But if that, think about it logically, if that reaction is not going this way, this ladder is going to be moving. We don't want that. And we'll just call that point A. So we're going to call this reaction AH and reaction AV. We good so far?
Yeah.
Yeah.
All right. So what's happening at the top? We said that was smooth. So what is that implying?
Would it be just to the right?
Okay, so why are you saying that?
A roller?
Yeah, but a roller could go up, down, or left, right, but you told me specifically that it's going to the right.
Because the wall is vertical.
Right, so the force has to be what?
Horizontal.
Well, it has to be, yes, normal. It has to be normal, correct. So normal is the same thing as horizontal because it's 90 degrees to the surface over which it's rolling. So perfect. What you told me, and this is completely correct, because this wall is here, this guy's free to move up and down along it, but it can't move this way, okay? So what we're gonna do is we're gonna indicate a reaction, and you said you want it to go to the right?
Yeah.
Okay, so we're gonna go to the right. You want it to go this way, to the right?
Yep.
Okay, so that would be reaction, we'll just call that B. So that will be reaction BH. Okay? So the other thing we should do, and think about this, is anytime you do these problems, give yourself a sign convention kind of thing going on. So I'm going to assume that anything that's up or to the right or clockwise is positive. Okay? Sound good? So we have now everything in place by our free body diagram. Okay, so remember this has done right here a whole chunk of our work. So now all we need to do is apply the equations of equilibrium. So I'm going to start out with sum of forces in X. I'm going to put it down here. Hopefully you guys can see this okay. Sum of forces in X have to equal 0. So in the X direction, what do we have? Our AH, everybody agree with that?
Yeah.
And we've indicated that it's going to the right, correct? Plus RBV, or I'm sorry, RBH. Anything else in horizontal direction? That's everything, right? So those guys have to equal what? They have to equal 0 by equilibrium, correct? Can you guys see a problem here? Anybody? In order for this to equal 0, they either both have to equal 0, which is impossible, or one of them has to be negative. Right? Everybody see that? So what that means is our AH is going to be equal to a negative RBH. So what that indicates, and we'll figure this out, that we went the wrong way with one of these. Okay? Not a big deal, though. We're not going to worry about it. All right? Is everybody okay with that?
Yeah.
All right, so now we can do a sum of forces in Y. So there's going to be a lot more going on in the Y. Sum of forces in Y have to equal 0. So in Y we have RAV. That's going up, minus 180, minus 150. Do we have anything else going on there? Anything else in a V direction or in a Y direction? So we've got this one here, that one here, and this one. So that should be it. So all of these have to equal 0 by equilibrium. So what that tells me is RAV 150 plus 180 gives us a negative 330. It's going to come over as a positive 330. So the unit on that, I didn't say expect that out. We'll just say that's pounds. So I'm going to call this pounds. 330 pounds. What does the positive indicate? Since this was positive, what this indicates is that we acted this correctly. So RAV is actually up 330 pounds. Is everybody good with that?
Yeah.
Well, we still need to do what? We haven't resolved what? We've not resolved these guys, right? We know that they have to equal each other, and we now know that they have to be opposite directions, but we don't know their actual value. So how do we do that? Got one more equation. What can we use? Sum of forces in X, sum of forces in Y, so the only thing that's left is a moment, correct? Yes?
Yeah.
All right. So sum of moments. We're going to do a sum of moments. We know sum of moments about any point have to equal 0. We're going to define clockwise moments as positive. We want to be smart where we take our moments. Where's a good place to take moments? We want to cancel forces that are unknowns. Nobody has a suggestion?
.4 feet away from the pin.
So you're saying here
Yeah.
or here?
Above.
Okay.
Above the 180.
Now, you're canceling out a known there. Do you want to do that? Because you're going to have 1, 2, 3 unknowns. Well, that one's actually known, but if I take a moment here, I'm going to wind up with 2 unknowns in that equation, and it's not going to solve.
Okay, then below that, I guess.
So how about here? Why is that smart right there?
That's where the pin is?
Yep. And also, look, this guy's line of action is coming through the pin, so is his. So those two are gone. So what I'm going to be left with is this moment and that moment and that moment. And that'll solve because I'll have this guy here. Now I could equally take it up here, okay? It would knock out RBH. I would solve RAH, but I would have to use RAV as part of the solution. The problem with that is if I blew this right here, then this moment will be wrong. So if I can not use something that I've already calculated, that way, if I make a mistake here, I could still get my moment correct. Does everybody see what I'm getting at? So from my standpoint, B would not be as smart as A, okay? But either one would be valid. But this one would not be because you would have too many unknowns in that equation, okay? So if we say let's going to take it at A, what that says is we're not going to be dealing with RAH or RAV because they're both gone. So taking a moment at A, what's the first moment? We have a distance of 4 feet times a force. So that's going to be 4 times 180. And that's tending to turn this ladder clockwise. So this is actually a plus. Okay. Does everybody see that moment? That's the first moment. The second moment would be based on this force over this distance. So this distance is 4 plus 2, 6, times 150, tending to turn this ladder clockwise. So that would also be plus. That's a plus rotation, 6 feet times 150 pounds. Okay? So then we have this guy. Who can tell me what the distance is for this? And its rotation. What is the distance to RBH if we're sitting here? No one can tell me a distance? Well, it's either 8 or it's 10. I'll give you a hint. Is anybody out there? Okay, well, it's going to be the perpendicular distance, so it's 10. A lot of people would look at this, and this is where you really have to be careful and call this 8, okay? So the perpendicular distance through this point is actually 10. So the rotation would be plus, the distance would be 10, and we would be left with RBH. And all of that then has to be equal to 0, all right? So this should be solvable. You got 4 times 180 plus 6 times 150. So I get, when I do this math here, I get 1620. So what this tells me is that RBH is going to be equal to a negative 1620 divided by a positive 10. So that gets me negative 162, that's pounds. So what is the negative sign saying to me? Is that RBH is not to the right, it's to the left. So when you plug negative 162 back into here, a negative times a negative means that RAH is equal to a positive 162, and it's acting this way, which should make sense. So this guy, RAV is 330. He's carrying all the load vertically, and this load is distributed between these two, one going left, one going right. So this isn't a whole lot different from a parallel problem, and we did not have to use the concept of transmissibility to solve this. Questions? Anybody have a question?
Nope.
We're good? Anybody else? As you can see, you can make a mistake with your direction of your vector, and it's not a problem at all as long as you're consistent. So when I made the mistake here, it didn't matter because when I plugged that into the negative here, the negative times the negative, it corrected itself. Okay. So get used to that. That's not going to be an issue. All right, so we're going to take a look at a one that's a little bit more involved. Give me a few minutes. I'm going to clean this guy up. And we're going to have a bracket that's kind of a cross-arm bracket. So give me a minute to draw it here. And I'm going to draw it really, really very simplistic. So I'm going to have a bracket right like this. And it's going to have a cross arm. Something like this. And it's going to have some vectors acting on it. So there's going to be a vector acting down here. We're going to have a vector acting here. And we're going to have a vector somewhere here. Okay. So let me put my indication. This guy's going to be acting down. This guy's going to be acting this way. And this guy's going to be acting like that. Let me draw. So we're going to have a angle off of this. So we're also going to have, let me draw a figure here. Okay, there's a roller here. And I'm going to have a, let me see if I can do this one here. I'm going to have something going on over here. Okay, so there's my free body. Now let me put some numbers here. So we're going to call this, oops. Okay, so this is 400 pounds. Everything will be in pounds. I'm not going to put the unit right now. That's 800. This is 1,000 pounds acting at 30 degrees. It's 5 feet from here to here, 2 feet from the vector to the cross arm, 3 feet from the cross arm to the roller. And this cross arm is 2 up and 2 down, okay? So it's equidistant, 2 this way, 2 this way. And so we have from this to this, it's going to be 10 feet because we have 5 plus 2 plus 3. So we're going to call this A. and we're going to call this B. So what we're going to want to do is solve the reactions at A and B. Okay. So what's the first thing we need to do here?
Free body.
Basically, we have that, but what do we, that's correct. So when we say the free body, what we need to do is model what? These guys, what are these called?
The forces.
No, these are support reactions.
Or, yeah.
Okay, so we're going to model the support reactions. So what do we have going on at A? What is this indicating?
So there should be 2 reactions, right?
Yes, because this is a pin, right? Okay,
Yeah.
so good. We're going to go ahead and let's get rid of that. We're going to replace those. Okay, so what do you think's going on? Left, right, up, down? You're going to have 2 of them, right? One's going to go left, right. I'm going to just go ahead and I'm going to indicate them. You guys tell me which way you think. So there's one here, right? And there's potentially one going this way. So this one can go up or down. What do we want to do? Up or down with it? Remember, it really doesn't matter.
Up to the right.
Okay, up and to the right. Okay, so we're going to call this up and to the right reaction. And we're going to designate this R, AV, and R, AH. Okay. So if you didn't see that that was a pin and you went and did that something different, then you're going to have problems. Okay. So what do we have over here? This is a roller, correct? What this is telling me is that it's free to move in this direction, but it's not free to move in this direction. So that means that we have to have it going, it has to be restrained either up or down. That's what that's saying. So I'm going to go ahead, you guys, let me go ahead and delete this. And you guys can kind of tell me what you think you want to do. I'll get the line drawn on there. And again, don't struggle with it. As long as we're close, it's all, in other words, not close, but as long as we get this direction right, that line of action, we can go up or down with it. So what do we think, up or down?
Up.
Up, okay. So we're going to go ahead and call this up, and we'll call this reaction RBV, okay? So that's kind of your first step. I'm going to get rid of this designator because we don't really need those. Okay, so the other thing we have here is a vector that is not parallel with X or Y. So what I definitely recommend with this, we want to get rid of this and replace it with its components. Because when you start doing your moment, if you don't do that, that becomes really a problem, okay? So I'm going to take the cosine of 30 times 1,000 to get the vector going this way, and the sine of 30 times 1,000 to get it going this way. Does everybody agree with that, what I just said? Cosine of 30 times 1,000 should get me the vector acting this way. Sine of 30, 1,000 should get me going that way. Okay? So I'm going to take 1,000 cosine 30. I get 866. So give me a sec here. I'm going to go ahead and erase what I've got here. So anytime you have vectors that are not horizontal or perpendicular, or horizontal or vertical rather, excuse me, anytime you have that, the first step is to break those down. You may actually have several that you need to break them down with. So let's see, I'm gonna put this guy, I'm now gonna replace that with a vector doing this, and one that's doing this. So I just took the cosine of 1,000, or the cosine of 30 rather, times 1,000, and this gave me 6, so the sine is going down. Let's see, we've got 1,000 sine 30, I get 500. Okay, so on non-concurrent, actually on any problem, the first thing you're going to do is if you have vectors that aren't horizontal or vertical, break them down. Okay, that's a good step. So now we have a complete free body diagram, and everything should analyze pretty nicely. And in this one, I don't believe we're going to have to use transmissibility anyway. So let's see what we've got going on here. Now, you do have a lot of vectors, so make sure that as you get into these types of problems that you're really paying attention to what's going on there, okay? So what I have, I'm going to do a sum of forces in the x. Sum of forces in the x. I'm going to start out with x. And in the x I have, well, let's do this too. We should really do this, get my sign convention going on so that you're aware of that, okay? All right, so in the x, we have RAH, whoop, that has to be 0. We have RAH. What else is going on there in the x? Plus 400. Minus 866. Anything else horizontal? Looks like we've covered everything, haven't we? This one, and this one. So all of this then has to equal 0. So that you can see that this one resolves direct. So we have 400 minus 866 gives me a negative 466. It's going to come over as a positive. So that's great because that indicates to me that we set this up initially right. So this is going to be 466 pounds, and the positive indicates that it's going that way. So we made the right solution on that. Okay, so that one resolved easily. Now we've got two vertical unknowns, and they're going to be a little trickier. So let's come down here. Summation of forces in the y have to equal 0. So in the y, we have RAV, and we indicated RBV up, so that's also a plus direction. So both of these are plus, I just didn't put the plus out here. So now we have negative 800, negative 500. Any more verticals? We already took care of those. Two unknowns, and these two acting down on this bracket. So it looks like that's our complete equation. Unresolvable, but it does tell us that when we add these two guys together, that's going to get us 1,300. So negative 1,300 is going to come over as a positive 1,300. So what that tells us is that the sum of these has to be equal to 1,300 pounds, but we don't know what the distribution of this is. So in order to determine how much this is carrying and how much that's carrying, we're going to have to do a moment. If you guys had to guess, can you determine which one of these is actually carrying more load? Anybody have a suggestion? Just looking at your diagram up here. If I had to guess, the 500 is closer to the RBV than this. This one's actually right in the middle. So I would say that this is going to carry a bit more load than actually that will. Okay, so let's see if that's true. So, and I don't really care about that, but sometimes I like to think about that because that way when I get numbers, they should make sense. So sum of moments about any point have to be equal to 0 by equilibrium. So where's a good place to take moments now? Remember, we're trying to cancel out unknowns. Ivan, where's a good place to take moments? Irvin, sorry, not Ivan. Irvin. Are you there? Irvin, you got an answer or a suggestion? No. All right. Anybody? Mitch? All right. Well, I'm going to take moments a day. So if we take moments about A, what we would have starting here, moments a day is going to knock out RAH and RAV. And so all of the rest of these are going to have to be dealt with in this moment equation. So this gets to be a bit of a messy moment equation. So what we're going to do is look at this 800 first, and we notice that there's a 5-foot distance to the 800, and it's tending to turn this guy clockwise. So we're going to call that a plus 5 times 800. Okay. So for this one right here, this one's tricky. A lot of people would tend to call this 7 feet, but it's really 2 feet. If you take this guy's line of action over here, it's 2 feet. So this would be 2 feet times 400, and that's also tending to turn this guy clockwise. So that's going to be plus 2 times 400. That really tends to be the hardest kind of thing you deal with there. All right, if I look at this vector, 500, he is 7 feet over 500, and he's also tending to turn this clockwise. So what we're going to have here, that's going to be plus 7 times 500. And then this guy is also 2 down. So line of action, that's 2, also tending to turn it clockwise. So this is going to be plus 2,866. So the only thing that's left now, we've got 1, 2, 3, 4, each one of those moments. So this guy is 5 plus 2 plus 3. So this is 10 feet from here to here. So that's going to be a negative 10 RBV. And all of this is equal to 0. I'm going to put my 0 out here. So we should be able to solve this. You have to be careful with your math, but let me go through and do mine. So I'm getting 10,032 when I do the sum of these products. So what that tells me is RBV, if I bring this guy over as a negative, it'll come over as a negative 10,032. And I'm going to divide that by a negative 10. So negative divided by negative gives you a positive. So that tells me that this is going to carry 1,003.2 if you want to. You could probably just drop the point. And that positive indicates up because we initially said it was up. So what happens over here when we bring this guy RAV, we have 13 minus 1,003. And that gives us a positive 296.8. And again, you can round some of those up, but that's also a positive. So what we see here is lot less load here that this is carrying. What I said initially, when I looked at this, I said, because this guy's kind of out of balance here, and I didn't even think about these too much, but this guy's carrying a whole lot more load than this one, right? So that's your solution. And again, transmissibility was not needed in that problem. So that was a good one. All right. Any questions?
So the answers that you were looking for, are those RAV, RBV, and RAH?
Absolutely.
Okay,
So what you're looking for is unknown reactions, okay?
okay,
Here's the thing, we are not like doing resultants any longer, okay? That was just a technique to kind of do things. What we're really looking to solve now is unknowns, okay?
okay.
And as exactly what you said, that you got here and here. Now, you have to recognize that this was a pin, right? So you have to know that you had two reactions here.
Yeah,
If you modeled that as a roller and a roller, you'd be wrong. For one reason, it should tell you that, but if you only had, if you said this was a roller and this was a roller, there would be nothing here to resist these two guys. So this would be skating in that direction, you know, with that amount of force is kind of what's happening. So you can get into a mess if you don't model your reactions right. So it really comes down to that. And also your free body in general, you know, breaking forces down. Can you see how tricky this moment can be, especially when this guy's doing this way?
yeah. I was a little confused on which parts you were using.
Do you see that now?
5,800.
These are pretty cut and dried, aren't they? The 800 and the 500. You
Yeah,
see, you clearly see that this is 5 times that. This is going in a perpendicular direction, right?
yeah. Those ones I was fine with. It was like the 866 and 400. I was a
Okay,
little confused
if
on.
we take this line of action and just following back here, right?
Yeah,
Isn't that 2 feet above it?
yeah.
Okay, you have to kind of think that way. Okay,
Oh, I see.
okay. It's no different than what's going here. This, for some reason, and I'm the same way. This is real easy to see. Where this one gets a little trickier, and so does that one. So you have to kind of just think about that. But remember, the distance is always perpendicularly measured to the force's line of action. Okay. So if we bring it back here, you can see it's 2 above it, and it's 2 below it. But you also then have to think about which way is it turning. Okay. Does that make sense?
Yeah.
All right. Let's do another one. Okay, shall we? I'm gonna do a truss problem, but we don't have to worry about the truss. So what I'm gonna do is let me clean this up. And after we do this, then I'm gonna see if there's anybody has problems out of chapter 2 or 3, and then you can finish some of these, and then we'll take a look at some of those on Tuesday or Thursday rather. Excuse me. Okay. So I'm going to do this problem, and give me a sec to set it up. And this is what we would call a truss structure. And you're going to see trusses in chapter 4. In fact, it deals not exclusively with trusses, but quite a bit with them. Give me a sec to set this guy up and draw it up. And let's see. Yeah. I'm not going to draw all the truss structure. In fact, this is in your book. I'm doing the problem right in your book that's on page 82. So if you want to follow along with that, you can. Let me just do that here. Let's see. Draw that out. Now I'm going to cheat a little bit as I draw this, so just to simplify it. Okay, so this truss has internal structures into it. We're not going to really worry about anything. Okay, that's the one thing you can just kind of really make it simplified. That's what we're going to do. So we have two loads acting down. One is at 5 kilonewtons. And the other one is at 15 kilonewtons. Now we also have another force coming in at an angle. Like this. So he's loading this truss diagonally like that. And this is a 2 kilonewton force. And it happens to be 45. Okay, so this is 3 meters. They've got 3 and 3 in the book, so I'm just going to call this 6. And then this is 3 here. We're also told that this truss is 3 meters this way. So it's 3 meters high. And we're going to see trusses a lot in chapter 4. In fact, what we're going to be doing is analyzing all the forces through that truss. But all we're looking at on this case is reactions. And it goes back to your question, Max, what are you solving? And here we're just solving reactions. Okay. All right, so there's my picture. Now I have a pin over here and a roller over here. Okay. So I'm just going to go ahead. The roller is such that this truss can freely move in the left and right direction. So we know that this roller is going to have to be reacting up or down. Okay. The pin also, it's a pin, so it's going to bring 2 reactions to the table for us. So we're going to have one this direction, up or down, and the other one is going to be reacting left or right. So I'm going to go put this like this. Okay. And I'm going to describe my convention over here. Up to the right and clockwise is going to be positive. All right, so this is the reaction at A and the reaction at B. So we need to model this. So over here at B, what do we think? Do we want to make that up or down? So this is, I put my reaction in here. I just didn't put its direction. Anybody take a crack at what they want to call it? I'm going to call it up. R, B, V. And I'm going to say up on this guy, R, A, V. And I'm going to call this guy R, A, H. So do keep in mind, if you make a mistake on these, it's not a big deal, okay? It will correct itself. So we also have this vector here that's acting 2 kips, or 2 kilonewtons, excuse me, at 45 degrees. So what do we want to do with this vector? You want to get rid of this, okay? You want to get rid of this. You want to break it down into its components. And this is nice because it's 45. What that tells me is the horizontal component, which is acting this way, and the vertical component, which is acting this way, are going to be the same. So I'm going to go ahead and delete this, and I'm going to replace it with its 2 components. So I know I'm going to have one component coming this way. Other component coming this way. So we've got 45 cosine and sine, same number, right? So 2 times the cosine of 45 I get 1.41. So this guy is 1.41, and this guy is 1.41. So the big step, whole process, is right here in this diagram. And notice we don't really even care about what's going on here. Technically, we could draw that like any shape. It doesn't matter because we're not looking at any of the internal structure on this truss. In chapter 4, it's going to be all about what's happening here, what's happening here, what's happening here. But right now, we're just solving reaction and reaction, okay? If you can't solve reactions when you get into chapter 4 and the other chapters, you're never going to be able to get any of this. So this is really important stuff right now, okay? This is setting the stage for all of that. Is everybody okay with how I've modeled this before we move on? Any questions? And it's truly a non-concurrent because this guy makes it a non-concurrent essentially. Otherwise, you just have a parallel force system. So parallels are really, really, really similar to the non-concurrents. All right, so we're going to start out. Let's do our solution.
Actually, real quick, I'm a little confused. How did
Say that again.
I'm a little confused. How did you get 1.41?
Okay. Did you notice what I had in there before? And I didn't put the angle there. That was a 2-kip load coming down, or 2 kilonewton.
Oh, okay.
And it was at 45. Do you have your book?
Yes. What page is it on?
This is on page 82. It's
Okay.
example 3.8.
Got it.
Okay. Now, do you notice how that picture is a lot more complex than mine?
Yeah, but I see what you did.
But you don't need to mess with it, see?
Yeah.
So you can just kind of, on these problems, we don't care about any of the internal structure. And since this vector was coming down at the 2 kips at 45, I just broke him down into components. Okay?
All right.
So anytime, and I'm say this again, anytime that you have vectors that are not horizontal or vertical, your first step, probably even as much as modeling reactions, get rid of those vectors, okay? Break them down to their components so that when you get into doing your moment equation, your moments are going to smoothly solve. Otherwise, it becomes a real mess, okay?
All right.
All right, cool. All right, so we good to go on now?
Yeah.
Okay, so sum of forces in X, sum of forces in Y, and sum of moments should solve this. So we don't necessarily have to apply transmissibility. That's kind of, you don't use that too often, but there's a couple of problems on in the book, actually, I'll show you that you need to do this. So sum of forces in X we have, and remember, in the X direction, if it's to the right, it's positive. So we have RAH. And that was the way I modeled it. So I'm saying it's going to the right. These are all vertical forces, so the only thing we have there is that negative 1.41, and all that then has to equal 0. So beautifully, this just resolves right out. RAH is 1.41, and that would be kilonewtons because that's the base unit. And since I indicated it was going this way, and since it's positive, that's what it tells me. Okay? So that was a really quick, easy solution. Nothing to that, right? So what we now are going to look at is sum of forces in the Y. Sum of forces in the Y have to equal 0. There's a lot more going on in the Y. So we have RAV, and I indicated it going up. So from my convention, it's positive, plus RBV, which again, I also indicated that one going up. So I'm calling him positive. And then we have -5, -15, and a -144. Now, here could be a potential pitfall. if when I did these breakdowns and I put this the wrong direction, if I put him up, I've blown that in that problem. So you really have to kind of watch that when you're doing those vectors. Make sure that when you break your vector down, you're putting it in the right directions, okay? So everybody agree with what I got? I got these guys down, negative, 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 and then these are up. So I think that takes care of all of the vertical components. So this will give us not an answer, but it gives us a partial answer. So we have 5 plus 15 plus 1.41. They're all negatives. Oops. 5 plus 15. So I get a negative 21.41. That's going to come over as a positive. So I get R AV plus R BV. So that comes over as a positive 2141. So we do know that these two reactions are going to carry between them a load of 2141, but we don't know what the distribution is here, okay? So the thing that'll tell us that distribution is always going to be your moment equation. So we're going to do a moment. We really have to be careful with the moments, but let's see. Moments about any point have to equal 0 where clockwise moments are positive. So again, we want to be smart. We want to knock out unknowns. And, you know, just about 90% of the time, it's either going to be one of that reaction or that reaction. Those are going to be the places you would want to take moments. For instance, if I took a moment up here, I'm going to lose these 3 vectors and still wind up with 3 unknowns. So that wouldn't be great. So I would say A would be a good place because you're going to get rid of these 2 guys. And even though we know this resolution, again, if we use that and it's wrong, like if I come over here, well, actually, if I come over at B, RAH is going to be gone anyway. So really, either A or B is going to be a good location. So unless anybody has well, we're going to do it at B. Instead of doing it at A, we always do it at A. We're going to do it at B. So I'm going to take a moment at B, okay? So when I take a moment at B, RBV is gone and RAH is gone because his line of action comes through the moment. So I'm going to be solving for RAV is what's going to happen, okay? So I'm going to start here, 3 meters times 15 kilonewtons, and it's turning it counterclockwise. So that's going to give me a negative rotation of 3 times 15. So that's this guy times that. Rotation is like that, okay? So if I look at this one here, that's going to be, well, let's look at this one. This one is also 3, also clockwise or counter. So that's going to be a negative 3 times the 1.41. All right. If we look at this guy, that's 3 at 1.41, and that's also turning it counterclockwise. Okay, so now let's come back over to this 5 kilonewton load. So we have 3 plus 6, that gets me 9. So we've also got a negative rotation. So we've got minus 9 times 5 kilonewtons. All right, so this vector, this vector, this vector, and that vector. So there's that moment, that moment, that moment, and that moment. And notice they're all tending from point B, they're all tending to turn it counterclockwise. So they're all negative rotations. Negative rotation, negative rotation, negative, and negative. So this guy is going to be turning it positively. And we have 3 plus 3 plus 6, so that gives us 12. And that will be a positive 12 R AV. And all of that then will equal 0. So this will resolve. And notice all of these guys are going to go to a negative number, but when you stack them, they're going to come back to, or when we bring it over to the other side, they'll be positive. So that's good because that tells me I'm going to be all right with my solution. You guys are going to have to check me on this. I'm going to check my number. I don't agree with what I got. I'm going to. Okay, I got 98.46. So that's a negative 98.46. It's going to come over as a positive 98.46. And we're dividing that with a positive 12. So that gives me 8.2 essentially. That would be kilonewtons. So we indicated AV going up. This is telling me it's positive. So that indicates that my direction was right initially. So when we plug that into here for AV, that tells me that our BV is going to be equal to 21.5 minus 8.2. I get 13.2 kilonewtons, and that's also acting up. So the distribution is BV is carrying a lot more of the load than AV. Again, you kind of look at this and it kind of makes sense. There's a lot more going on over on this side than there is that side. So really it's just how it's balancing. All right. So hopefully you'll see these guys aren't that tough. If you can handle parallels, then really these are about the same. If you have your book handy, I will show you in problems where you might need to use transmissibility. Problem 18 out of chapter 3, page 101. I'm going to just a hint on that one. You typically need to use transmissibility to solve that. All of the rest of those, from 14 up to 20, I think, those are all going to be pretty straightforward, just like we did here. Okay? So let me open things up to any questions, and I'll be glad to solve any problems that you have from chapter 1 or chapter 2. We did quite a few the other day in class, but if there's some that you want to take a look at or revisit, we could do that. Does anybody have one they might like to look at? We can even do some of those out of there if you want, like chapter or like maybe 16 or something. I'm set up to do it, so. I'm going to go ahead and clean this up and see so that if you do decide you want to do a homework problem. Okay. So what problems? You'd like to look at any problems? Anybody seen any problems that they've worked on?
None that I can think of.
I'm sorry, say that again.
There's none that I can think of, really.
Okay. All right, well, if nobody has any questions, then I I think we can pretty much wrap this up. I will go ahead and record this now, or I'm recording it, so we'll stop it and I'll format it and get it published up to the web page, to YouTube rather. So Thursday, we're going to be doing a test. Okay, this will be our first test, and it's over primarily Chapter 2 and Chapter 3 questions. So there's only a few that you need to do out of Chapter 3 because we did a lot of them the other day, but problem 15 up through 20, just concentrate looking at those between now and Thursday. We'll take a look at them on Thursday morning. Okay, so we'll start at 8 o'clock. I'll do whatever we need to do, but we should be able to get started with that test by 9. And that test really shouldn't take more than 2 hours. Okay, and you can count on 3 to 4 problems. Primarily, like I said, they're going to be Chapter 2, Chapter 3 type problems. And I'll let you guys create like a cheat sheet if you want to set that up. Just like a 8.5 by 11 sheet of paper, put some equations down on that you would think you would need. And maybe a problem or two if you want to. And you'll have a calculator. So if you want to bring a straight edge to draw with, that's always helpful. Equations that I would put on your cheat sheet would be the equations for like sine, cosine, tangent. So make sure you know that or have that. The sine law and the cosine law, because you may need to use one or both of those. Okay. And really, as far as the equations from Chapter 3, it's just summation of forces in the x, summation of forces in the y, and summation of moments. But do make sure that you understand the different types of force systems, the concurrent, the parallel, and the non-concurrent, okay? And if you want, that little chart on, let's see, out of Chapter 3, page 63. You need to have those memorized, or you can write those down on your little cheat sheet so you'll have those ready to go. Okay, so that's all you really need for Thursday. And then, like I said, if you have questions, we'll answer them then. I would suggest this too. You know, I have office hours tomorrow from 8 o'clock until 1 o'clock. That would be a great time if you had a question specifically and you wanted to have a Zoom conference with me. Just shoot me an email, or you can set up an appointment through Starfish. Okay. And otherwise, we'll plan on working this stuff on Thursday morning. We'll be ready to go. Remember, we're in room 405, I believe, of the ATLC. Okay. Anybody questions?
Nope.
You guys have all been really quiet. That's, I have to say, that's really hard to lecture when I don't get much input, but hopefully that you guys are catching it, okay? But if you do have a question, make sure you follow up with me. I will be getting into that deck project. I just decided we're just going to wait. We're going to get this first test out of the way. I'll probably go over that deck project next week. Well, I definitely will. We'll get you guys started on that. And next week, Chapter 4 gets a little rigorous, okay? It's not like, the concepts are not hard, but sometimes the doing of it is. So we're going to be looking at truss analysis, dealing with 2 broad types of methodologies. One is called the method of joints, and the other one is method of sections. So next week, we'll be looking at that method of sections stuff, or joints, excuse me. All of that's going to be dependent on how well you can do reactions. So spend some time on Chapter 3, okay? And make sure you know how to do these reactions. And questions. Like I said, I'll be here tomorrow. I've got my office hours, and then later in the evening too, I'm available, I'm sure. So just if you have a question, send me an email request or something, and we can make sure it happens. Okay? Anybody questions in?
All good.
All right, good. Well, you guys spend the time. And I'm going to go ahead and stop this. And I'll be here. So if somebody wants to, if anybody wants to go over anything individually, we can do that. I just want to stop the recording right now, okay, and get that going. So I'm going to go ahead and stop the recording. And then if anybody wants to stick around, I'll stick around for a little bit. And that way you can ask questions.